feel like it's really loud. All right, cool. Welcome everyone to Space Drafts 115. I'm Noah. I am a third-year grad student, astronomy grad student at University of Arizona, one of the organizers of this event. For all the newcomers here, and I know we have a few, welcome. Space Drafts is Tucson's version of Astronomy on Tap, a network of events for sharing astronomy with you, the public, in bars and pubs around the world. And so every show is a bit different. How ours works is that we have two 25-ish minute talks with a 20-minute intermission in between. In both talks, there should be a trivia question, and the speaker you can raise your hand to answer it, and the speaker will pick someone. If you get it right, then you win a free bit of merch from our merch table back there. And speaking of our merch table, we have a bunch of Space Drafts themed stickers, posters, things like that. Unfortunately, we are cash only, and donations are also greatly appreciated. And so, here to talk about searching for life on other planets is University of Arizona Planetary Sciences grad student, Searra Foote.
Hello, everybody. Is this an okay volume for everyone? All right. Thank you so much for being here. I'm so excited to talk about space with you here tonight. Thank you so much for the introduction. So tonight we're going to be discussing something very exciting, humanity's longest expedition. Are we alone? I'm sure that's something we've all pondered at some point, whether you're a scientist or just a science lover. So I would like to take a little survey of the crowd before we start. So raise your hand if you think that we indeed are alone. There's no life out there, no chance. We got to be the only ones. Raise your hand if you think that. Okay, all right, we got a couple in the crowd here. Raise your hand if you are hopeful that there's life in the universe, but you're not really sure. Amazing. We got some more people there. And raise your hand if unequivocally you're like, absolutely, there's got to be something out there. Our universe is so large. Absolutely, we're not alone. Raise your hand. Amazing. So while I can't give you the answer to that question today, I am here to talk about some of the different questions and methods we use to sort of evaluate this larger question of, are we alone? So I'd first like to orient us on a little scale of the universe here for a second. So we are in the Milky Way galaxy. So our trivia question, how many stars are in the Milky Way galaxy? Is it A, only the sun, B, hundreds, C, thousands, D, billions, or E, trillions? Okay, raise your hand if you think you have an answer. Okay, right in the back there. D, that is correct. Congratulations. So it is estimated that there are maybe 100 to 400 billion stars in our galaxy alone. So this here is a simulated picture of our galaxy. And this is our Milky Way galaxy right here. And we are here. So there's our sun in the middle, and all those little dots you see are other planets that have been detected. So planets, we have planets in our solar system, we have 8 of them. Outside of the solar system, these are called exoplanets. So these are planets that orbit other stars. And just a quick note here, this is the NASA Eyes on Exoplanets software. It's free to download, and you can explore the different types of exoplanets that we've discovered. So this here is just our galaxy. Now I'd like to show this image here of what is called the Hubble Deep Field. So this was taken by the Hubble Space Telescope. So this surveys just a small portion of our sky. It would be equivalent if you held a grain of sand in your fingers and held it out at an arm's length. And in this image alone, there's estimated to be about 10,000 galaxies. So that was from the Hubble Space Telescope in the 90s. Now we have the James Webb Space Telescope. So raise your hand if you've seen some cool pictures from James Webb online. Yeah, awesome. So we love James Webb and the beautiful pictures that it takes. This is taken in a similar area of the Hubble Deep Field. and it just shows how much clearer and how much higher quality pictures we can get with today's telescopes. Now, this is not necessarily to dunk on Hubble here. It just shows us that we need to appreciate where we came from in our technology and how we got to where we are today. And that's what I'm here to talk about. But speaking of appreciating where we came from, I would like to share this image. So this is indeed a picture of me in 2014 wearing my Yoda beanie. So this was the very first year I went to Phoenix Comic-Con, and now Comic-Con is a fun event. I love going. It's more than just pop culture stuff. They also talk about real science topics, and this was where I first learned about the subject of astrobiology and that you can actually make a career out of it. So I was very excited that day. And this is me just last year in 2025. So I am a grad student at the University of Arizona, and I also collaborate with NASA's Jet Propulsion Laboratory. And so every day I get to think about the question, are we alone? So moving forward, I would like to highlight some of the wonderful moments in time in humanity's longest expedition of trying to answer that question. And in doing so, it can orient us for talking about the future and some exciting space missions we have planned. So let's start out at the dawn of civilization. So let's go way back and talk about 10,000 BCE and earlier. Humans, look up. So the modern Homo sapiens, humans, what we are today, have been around for about 300,000 years. And for about as long as we have record, humans have tracked the stars, looked up at the sky, used them for navigation, agriculture, and calendars. The sky inspired wonderful stories of mythology and philosophy. And so this was the first time we really sort of looked up and pondered this question. So now, we move way further into human history. We look at about 350 BCE, so philosophy and debate. So people are starting to wonder, right? So we've looked up at the stars, we've sort of used them as a map, we're looking, we're telling stories about them, but we're kind of wondering more now. So around this time is when we have some ancient Greek philosophers that started asking some big questions, and some mathematicians that were actually able to start working out some of the answers to those questions. So we have Aristotle and Ptolemy, who decided that Earth might be unique, and they developed what is called the geocentric theory, meaning that the Earth is in the center, and the sun and all the other planets orbit around the Earth, and these planets move in complex paths. So later, this was of course proven false, but pretty wild at the time for someone to start speculating about that. So now we're going to move all the way up until 1543, where we get the heliocentric model. So this was proposed by Nicholas Copernicus, and this was when it was more widely accepted. So, of course, back in the day, people were like, that's kind of crazy, like Earth being the center of the universe, like, come on now. But at the time, it was considered that, this was not true. But it was finally able to be proven in the year of 1543, where we learned that Earth and planets orbit the sun, and this was very soon confirmed by other observations that we'll talk about in a minute, of Galileo in 1610 and Kepler. So, 1608, the first telescope. So the first telescope, believe it or not, was developed about 400 years ago, which is amazing to think about. And looking at some of those telescope images from today, it's amazing to think of how far we came. So the first telescope in 1608 was thought to have been built by Hans Lippershey in the Netherlands to use lenses to magnify distant objects. As you can see, there is a very distinguished looking man looking around with his little telescope. You might have seen them on pirate ships as well. But Galileo, however, was the first person to improve upon this telescope and actually use it to look up at the sky. So he discovered the moons of Jupiter, and he also was able to see the phases of Venus, which was able to, in fact, confirm that heliocentric theory. Next, we move to something that is very exciting. So the space age, the space race in the late 1950s and 60s. So this was around the time of the Cold War. Sputnik 1 was the first artificial Earth satellite to be launched by the Soviet space program in 1957, and the race was on. So we finally end up in 1969 with humans landing on the moon. If you want to, raise your hand if you saw this live. Wonderful, amazing, and now you're here today. Look how far we've come. So now we move into the more exciting territory. Discoveries are happening a bit faster here. In 1995, we have the first exoplanet confirmed. So as discoveries go, the first exoplanet might have technically been discovered in 1994, however it was orbiting a pulsar. But however, the first exoplanet discovered orbiting a sun-like star was 51 Pegasi b in 1995. So this was a really groundbreaking discovery. And so this was the very first time this exoplanet was confirmed, and that was only our first one in 1995. And now today, we have over 6,000 confirmed exoplanets. So this is very exciting. And 51 Pegasi b is considered a hot Jupiter exoplanet. So there's a lot of different kinds of exoplanets, and these are the easiest to study. They are big and hot, i.e. hot Jupiter. So now we start moving into the present. So we've had a lot of development going on. So we kind of move into some of our more modern telescopes. Maybe you've heard of some of these. This is not an exhaustive list of everything that's been launched, but just some really cool ones relevant to exoplanet studies. We had Hubble launch in 1990. So that was actually able to tell us the age of the universe, 13.8 billion years, which is pretty cool. And then we have Kepler and TESS, which was observing and detecting exoplanets. So that's where a lot of those numbers came from. And then we have the James Webb Space Telescope. This one was long awaited by the community. You might have seen some of those images as we talked about before, and they also observe the atmospheres of these exoplanets, which we'll talk about shortly. And we also have coming up Roman that will launch, the Nancy Grace Roman Telescope will launch in 2027, and we're very excited about that. But there is even more exciting things on the horizon. What is next? So we look to the future with the Habitable Worlds Observatory and beyond. So the Habitable Worlds Observatory is an upcoming NASA flagship mission that I'm very excited to tell you about. So my research will hopefully inform this mission. So, and as you can see, the tagline on the top, are we alone? So the Habitable Worlds Observatory is the first telescope designed specifically to search for Earth-like planets around sun-like stars, which is very exciting. Now, when I say Earth-like, what do I mean? So we want a terrestrial planet. So we want a planet that has a rocky surface. We want a planet that has an atmosphere. We want a planet that is maybe similar in size to Earth. That's what I mean by Earth-like. And, well, what is a habitable world? In fact, that is a question we're also still trying to answer. So, as you can see, maybe the question, are we alone, contains multitudes of more questions. So, when we think about what makes a habitable planet, I mentioned all those things. And one of those things that we can look at to learn more about a planet is its atmosphere. So before we can answer, are we alone, we must ask, how can we detect signs of life in planetary atmospheres? So we're going to talk about something called biosignatures. So biosignatures are chemical signatures in the atmosphere of a planet that could possibly indicate life. And so this was a spectra taken by the James Webb Space Telescope of the hot gas giant exoplanet WASP-39b, and this shows its composition of the atmosphere, what we call a spectra. So it shows the different wavelengths of light that are absorbed, and by studying that, we can study the spectra here to see where the dips are, and this is able to tell us what species is detected in the atmosphere. So on this planet, we have water, for example, so we have your water lines here, CO, carbon monoxide, CO2, carbon dioxide, and more. So this is what we mean when we say we're looking for biosignatures. So we're looking for what is in the atmosphere. And could that possibly mean that the planet could be habitable and could support life? But before we answer how can we detect signs of life in planetary atmospheres, we must ask, how can we find these Earth-like planets, right? We were talking about the universe is so big. How do we actually find these planets and get to them so that we can study those atmospheres? So with the Habitable Worlds Observatory, this here is one of the concept designs. So the Habitable Worlds Observatory is set to launch in the 2040s, but science is happening now. This was actually the first design they came out with, and what they're doing is they're testing different designs. They're now on what they call EAC 6, so that's the sixth design, so we've come a long way. But we're trying to figure out what is the best design of the Habitable World Observatory to detect planets and to look into their atmospheres. So the Habitable World Observatory will use a direct imaging method of detecting exoplanets. So previous studies such as Kepler or TESS use what we call the transit method. So looking at a planet going in front of its star and observing the dip in the light. And direct imaging is very important. So it's almost like taking a picture kind of the exoplanet, but we run into a problem. So the star is so bright and Earth-like planets are going to be fainter than their star and pretty close to their star. So it'll almost be like looking for a firefly next to a lighthouse. So how do we get rid of that starlight? So we have something called a coronagraph. So what a coronagraph does is it blocks out a pinhole of light from the star so that we can just make out the light of the planet. And by examining that light from the planet, we are able to detect it. And this is kind of important because not only that, but planets change in brightness as they orbit around the star. So that's also something to take into account. So we have all of these series of questions and things that we're considering. So what we're doing now, why we're starting so early with looking at these different designs, is to figure out what we need to do to, at the right time, be able to observe such a world and be able to study them. So in comes something that I work on. So I use this code. It's called ExoSims, Simulations of Exoplanets. And what it does is it takes into account a bunch of different things about your telescope itself. So what's the size of it? How big is the mirror? How does this telescope move? How's the orbit? What's the design of the optical system? What's the coronagraph like? How is it blocking that light? And it takes into account information that you give it about a particular planetary system. And what it does is it uses something called Monte Carlo mission modeling. So Monte Carlo basically takes all these huge factors into account and schedules a mission, like you're actually going through a mission. And what it does is it gives you hundreds of ensembles of planets, and it's able to tell you, based on everything you gave it, how many planets that you've detected. And while the number of planets is super cool, like what an awesome thing to predict, we also want to think more about their atmospheres, right? I was showing you guys that spectrum. We care about the composition of the atmospheres. So what we want to do is understand more about those atmospheres rather than just the number. So we move beyond how can we find Earth-like planets, and we want to move towards the question, well, for a particular architecture of HWO, in how many worlds does it successfully detect a biosignature in the atmosphere? So one of the biosignatures that I care about is oxygen. Oxygen is a very important chemical species, and I'm not saying if we find oxygen, it means we found a habitable planet. As I discussed, there's a lot of different metrics we have to think about when we're thinking about finding a habitable world, but that's just one that I particularly care about. So we want to sort of put this information into our ExoSims code so that we can learn how and where we might detect a particular biosignature. So we are using this really cool other code that is made specifically to look at the behavior of chemicals in the atmosphere and how they behave and how we can detect them. So this is just a schematic figure of what I am currently working on right now. It's true, the code is running as we speak. So this is what we want to do is in order to quantify how we might detect a certain biosignature, I said oxygen, for example, you would subtract the depth of that feature. So you saw that spectra before where we saw the different chemicals in the atmosphere. It's kind of like that, right? So you would tell it, okay, here is not detecting anything at all, and then, oh, boom, we've had an oxygen detection. So by this subtraction here, the code would then know, okay, you're able to detect oxygen. And we want to, in the future, think more about something called a signal, a signal to noise ratio. So how confident are we in that detection? And that is just one thing that we're hoping to build into that Exosems code so that we can learn more and better inform the Habitable Worlds Observatory. So tonight we have looked here at this Hubble Deep Field and seen how this image was transformed into this other beautiful image by the James Webb Space Telescope. We've seen me in 2014 just learning about astrobiology, and we've seen me today collaborating with Jet Propulsion Laboratory. And if those things can happen, I'm pretty confident that the Habitable World Observatory might just give us Earth 2.0. Thank you so much.
Does anyone have questions for Searra?
Hello, right here in the front.
So, on one of the first pictures we showed have a map of stars and detected planets. What
Yes.
causes their shape? Like, it seems like they're distributed in this very specific way. What causes that?
Yes, I can repeat the question. So they were asking, why do the detected planets appear in this weird shape? So that's an amazing question. So we are only able to look at a small part of our galaxy. So some of these, just because we've detected them doesn't mean that there aren't other planets here, right? So there's a lot. So we estimate that maybe for every one star, there's maybe one planet. So the reason why it's kind of like this awkward shape here is because that was the direction we were looking. So I mentioned Kepler and TESS. They went out and used the transit method to find these planets. And some of the planets are too faint to be detected or they're too far away. So that is why we see this shape here. So good question. Thank you. Yes, we have a question in the back. Yeah, that's a great question. So they asked what wavelengths are we going to be looking at for a future telescope. So for Habitable World Observatory, for example, I mentioned that it's designed specifically to look for Earth-like worlds around sun-like stars, but that's not all it's going to be doing. It's also going to be doing some studies of galaxies. So depending on what you're looking at, you need a pretty broad wavelength range. So it's going to be broader than James Webb. I believe it's going up to 1700 nanometers, I believe. So it'll be pretty big range, but it's still kind of being debated because they want to try to do as much science as possible. All right, any other questions? Yes, in the middle here.
Would you be able to use data from Gaia to help find targets to look at?
That's a great question. Thank you. So they asked if you're able to use Gaia or other data sets to sort of find targets to look at. And that is actually what we do with Exosems. So we sort of have all of these different data and we're able to sort of take those specific detections and those specific like archival data that we already have and use that to train Exosems and to use sort of as test cases because of course we can't say exactly where the planets will be, but we can use things like that to help us predict what the populations might be. All right, we gotta see two people here. I'll take this one in the front here. Absolutely, great question. So they asked, other than oxygen, what are some other biosignatures we might associate with life? One of those is methane. Methane can be kind of a tricky biosignature because it doesn't necessarily have only a biological origin. For example, like volcanoes emit methane, so that's kind of why we need sort of multiple lines of evidence. We also look for ozone, O3, or also carbon dioxide, CO2. So just to name a few. And there's one more question in the back. Yes. I'm sorry, can you repeat the name? Oh, Sukrit, yeah. So Sukrit Ranjan is also a professor at our university. I don't work with him directly, but we have like a planetary atmospheres discussion group where we all kind of talk about different things. So a lot of people, so I work with Dr. Tyler Robinson at the U of A, and he does a bunch of cool stuff. He's on the HWO team, which is super exciting. But yeah, I don't work directly with Sukrit, but yeah, our work sort of informs each other because we ask similar questions. Okay, we can take one more question. Yes.
You mentioned that you see the planet as it transits across the sun. So would we have to look at it parallel to the plane of orbit? Like, what if we were looking at the solar system from like a top? Because then we wouldn't see it transit, so it was harder to see.
Absolutely. So when we're thinking about looking at a planet, we sort of want to
Repeat the question.
repeat the question. Yes. So they were asking about when you're looking at a transit curve. So if you kind of need to look at the planetary system like right on the money, or how it's going to affect it if you're looking on top. So we actually have different views for these, like a face-on view. So like you're looking at it straight on, and then an edge-on view, like maybe you're kind of looking from the top down. So that can definitely, it depends what method you're looking at, but yes, with the transit method, you would need to be able to actually perceive the change in brightness in the star. So you would have to see that planet go in front to be able to see that dip in the light for that method. Okay, I think that's all the questions. Thank you so much.
Okay. I was going to start with, well, we should thank Steve again, but everyone just did that automatically. So, our trivia winner should go talk to us at the booth back there where Soleil's waving her hands. And just to remind everyone, we have our merch table back there, but I also want to highlight we are beginning to run low on some of our merch. So we are thinking about ordering stuff soon. And if you have ideas or things that you want us to get, or design ideas or things like that, we have a piece of paper and some pencils back there. Please feel free to give us ideas. And let's see what else. We'll be back in 20 minutes. Let's call it 8:20. And don't forget to tip your bartender. See you all in a bit. All right, everyone, we're gonna come back to Spacecraft 115. So our next speaker is postdoc Peter Stephenson, who will show us the aurora across the solar system.
Hey, hi everyone. Thanks for hanging around. So yeah, my name is Peter Stephenson. I'm a postdoc here at the Planetary Laboratory. And today I'm going to go on a little tour of the solar system. And our first stop, naturally, is here in Tucson. And so here we have Russell and Kevin and Doug out exploring the Sonoran Desert. When they were hanging around long enough, they went dark, and then they saw this incredible aurora that maybe you witnessed earlier in the year, maybe it was the end of last year, over the Catalina Mountains here. And so they thought, okay, this is incredible. Like, this is so beautiful. Where else can I go and see this and get a better picture of the aurora? And so they took a little journey from Kuiper all the way out into the Arctic Circle and end up over here at Svalbard, which is a really incredible place to see the aurora and has some amazing observatories there. And so Russell gets out his binoculars and looks up into the night sky, and this is the picture that he sees. And so this is really the typical northern lights that you expect, with this incredible green glow, this kind of constantly changing dynamic filamental structures, like truly incredible. I've not been lucky enough to see them yet, but hopefully one day I'll get the chance. So Russell's first question is, what's driving this? What's causing this aurora? And this story really starts at the sun. And so at the sun, we have a constant outflow of charged particles, so electrons and ions flowing outwards from the sun, which is what we call the solar wind. And when this solar wind flows out, it then reaches our planetary magnetic field and interacts with the magnetic field. And so what happens here is that we get, on the night side, these magnetic field lines get squeezed and stretched, much like an elastic band. And so when you build up more and more tension here, eventually that elastic band snaps and releases a lot of kinetic energy, and that accelerates particles and drives electrons into the upper atmosphere of the planet, at which point these electrons, these very energetic electrons, then collide with molecules in the upper atmosphere and give us this glow, which we know as the aurora or the northern lights. So the next question Russell has, why is it that colour? And so the colour of the aurora is really dictated by what's in the atmosphere. And so at our planet Earth, our atmosphere is mostly made up of nitrogen and oxygen. And so these are really what dictates the colours that we see. So the oxygen has two main colours that we see. In the visible spectrum, this kind of bright green glow, which is kind of your typical one, and then also a red line that you occasionally see a little bit higher up in the atmosphere. And then it doesn't come up super well on here, but your molecular nitrogen, when electrons collide with that, you get a lot more of these like purples and kind of blues that kind of appear a little bit lower down. And so kind of the ratio of these different colours and which ones you see as brighter is really dependent on the energy of the electrons that we have impacting the atmosphere. And so when we have less energetic electrons, they don't tend to penetrate as far, they lose their energy quite quickly, and so you only really drive emissions from the top layer of the atmosphere, and so that's mostly this atomic O layer, so you get more of this red line and the green line. But when the electrons are much more energetic, they penetrate a bit deeper down, and then you start to see more of this purple coming through. And so that's kind of the structure and the colours of the aurora that we see at Earth. But Russell wasn't happy with that. He didn't want to stop there. He thought, where else can I see the aurora? Where else can I see it in the solar system? And so now we zoom out from Svalbard and suspend your disbelief on how balloons work. We don't need to worry about that. But we're going to take a journey from Earth out into the solar system. And so our first stop on this journey is actually going to be at a comet. And not just any old comet. This is my favourite comet. So be nice. This is Comet 67P. And this was visited by the Rosetta mission, which was a European Space Agency mission. And it followed Comet 67P along its orbit for 2 years, from 2014 to 2016. And when it arrived, it found this comet which had a quite unique shape, which has been likened to a rubber duck. So this is our little space duck. But on arrival, Russell was really interested in what even is a comet. And so at the centre, we have this kind of solid part, which we call the nucleus, and this is made up of ice, rock, and dust. And crucially, it doesn't have any internal magnetic field, like what you would see at the Earth or Jupiter or many other planets. So there's no intrinsic magnetic field, and it's just this ice, rock, dust kind of conglomerate. It's probably not a conglomerate. I don't know any geology. Okay, so we've got the nucleus here, and when this is heated by the sun, the ices on the surface of the nucleus start to turn into gas, and they get heated up, and that gives us an atmosphere. And for comets, we call this the coma, and because comets are very light, the gravity is very weak, this gas is constantly escaping outwards. And at a comet, typically, what we have is mostly water and carbon dioxide. So these are our kind of main constituents in the atmosphere. And so here we have our little cometary atmosphere. This is just water for kind of simplicity. And when you bombard this with energetic photons from the sun, these water molecules start to break down into ions and electrons. And if we take these and try and separate the two, we then have an electric field between the two of them. So these different charges don't like to be separated, and you get a strong electric field between the two. And this is kind of what happens at comets. So when we create these electrons, they're very hot, they're very energetic, they really want to get out of there. They're trying to escape as quickly as possible. The ions, they're a little colder, they're a little slower, a bit more lethargic, they're hanging around. And so we get this situation where we have the electrons running away, the ions kind of more in the middle, and we get this radial electric field. And so when the solar wind shows up with its own ions and electrons, and they pass by the comet, these electrons and these ions from the solar wind, they have very different experiences. So from the perspective of positively charged ion, this electric field is like a big hill. So it's constantly being repelled. And so they slow down, they get deflected. It's really hard work for them. So they kind of try to avoid going really close to the center. But for these electrons, they're being attracted the whole time. They're getting pulled straight in. And that's more like this kind of skateboard ramp. And when they get really close to the center, they have a lot of energy, a lot of kinetic energy, which they can then use to break apart molecules, to drive emissions. And this is the aurora that we see in comets. And so if we kind of take this to some real data from Comet 67P, we have kind of two cases here, one where the solar wind's a bit stronger in blue, and one where it's a bit weaker in orange. And we're just looking at wavelength here. So this is basically the color of light, but we're looking at the ultraviolet range and then how bright things are. And we have a number of different emission lines from atomic hydrogen, atomic carbon, and atomic oxygen, which are just different fragments of these molecules that we saw in the cometary atmosphere. So we're going to focus on two of the lines, an atomic oxygen one and an atomic carbon one. And what we see is really that, okay, so on the right here, we have intensity versus time, and this is during kind of a solar event. So the blue line here is a model basically based on the solar wind conditions over time, and then the little crosses here are observations of these different lines and how bright they are. And what we see is that when the solar wind peaks, we get this really strong emission line because there's more electrons to throw into that potential well that can then collide with the atmosphere and drive these emissions. And so this is really our cometary aurora. And so this is just kind of a little graphic. So we've got electrons in the solar wind, they get accelerated, they break apart these molecules, and then we get this diffuse cloud. So because we don't have any internal magnetic field, we don't see the same kind of fundamental structure that you have at Earth, where you have these kind of shafts of light that are really tracing the magnetic field lines. This is much more like a diffuse cloud, and a little bit different in its nature. It's still very much aurora. So that's stop 2 on our little auroral tour. Now we go from the comet down to Jupiter, the big five. So Jupiter is, super magnetized, an incredibly interesting planet, and has this incredible aurora with so much structure, so much dynamics in it, and like incredibly interesting. And so the first thing we're going to look at is this little bright region here. And so this is actually driven by one of Jupiter's moons. And we're just in time for trivia time. So the question is, which moon is causing this bright spot in Jupiter's aurora? So you have 4 options: A, Titan, B, Io, C, Ganymede, or D, Europa. Any takers? Got one down the front. Io. It is indeed Io. So this is Io. And here we can see it here, but it's not the only moon that has a footprint in the aurora. So here you can also see little footprints of Ganymede and Europa as well. But we are going to focus in on Io and examine why is it so bright? Why do we get this incredibly bright spot in the aurora? And so this really starts from Io's volcanic activity. It's the most volcanic object in the solar system. It's constantly being pushed and pulled by the other Galilean moons and by Jupiter, so it gets squeezed, and this gives us a really dense sulfur dioxide atmosphere. And so, much like we saw at the comet, when you bombard this with high energy photons, you break apart this SO2 into a collection of ions and electrons, and this gives us a conducting layer in the atmosphere. And so, before we take this and pop this into Jupiter's magnetic field, we're going to take you back to high school. Electromagnetic induction, or magnetic induction. So the key thing to remember here is when we have changing magnetic fields, they're going to drive currents in conductors. So as we move this magnet, we're going to drive currents through the circuit. And this is very much like what we see with Jupiter and Io. So here we've got Jupiter at the center and Io with its conducting layer in its atmosphere. And so we're going to pop this into Jupiter's magnetic field and spin everything. And so this is kind of like a complex picture. There's a lot going on. So we're going to take it back a step, and we're going to look at it from a frame that's rotating with Io. So here you've got Io nice and stationary with its little conducting layer in the atmosphere, and Jupiter's magnetic field is constantly moving through it. So we have this constantly variable magnetic field, and what that's going to do is drive a current in Io's atmosphere. So where's that current going to go? So this is kind of what happens. So we drive the current here in Io's atmosphere, and then it connects along the magnetic field lines into Jupiter's upper atmosphere, and then back out. Now, current is a measure of positive charge. So if we're looking at electron behavior, the electrons are going to travel in the opposite direction. So this point here, where we've got the current coming out of Jupiter's atmosphere, is actually where the electrons are being fired and accelerated into the atmosphere, and this is where we get Io's really bright auroral spot. So not only does this drive this bright auroral emission, but it has other important effects to Jupiter too. So we're going to take a slightly simplified version of this circuit, and then in this kind of system, we have Io is really the battery that's driving the circuit, and then when the current goes through Jupiter's atmosphere, it experiences a resistance. So this is the resistor here, and when you drive a current through a resistor, it gets very hot. And so this heats up Jupiter's atmosphere. And really, this is heating it up in two spots, in the northern hemisphere and in the southern hemisphere. So we're injecting a lot of energy into the system from not just Io, but this kind of wider plasma cloud that extends quite far out into the kind of planet's magnetosphere. So yeah, we're injecting a lot of energy both near the northern and the southern hemisphere, and this is what we see at Jupiter. So this is the temperature of the upper atmosphere against latitude along the bottom. So this is the North Pole on the right, South Pole on the left, and then the equator down here in the middle. And this is very different to what we see at Earth. So at Earth, we'd expect temperature to be hottest near the equator, and then it kind of drops off as you go to the poles. But this is the opposite at Jupiter. And that's really driven by this auroral heating, which dumps a huge amount of energy near the North and South Pole, and gives us this kind of weird, these temperature peaks near the poles. And this doesn't just happen at Jupiter. This is very similar to what happens at Saturn. At Uranus, it's a bit of a muddier picture, which we'll kind of come on to later. But yeah, these kind of auroral circuits, driven primarily by Io, really drive the heating that causes this massive temperature gradient. So that gives us a brief tour of Jupiter's aurora. And now we're going to take our final step in the journey from Jupiter all the way out to Uranus on our final stop. So Uranus is a super interesting planet, but the last time we visited it was in 1986 with Voyager 2. So that's 40 years ago now. And why is Uranus so interesting? For me, I don't need to be sold on that, but for you, I guess maybe it's not self-evident. But first of all, Uranus's spin. So Uranus is super inclined to the ecliptic plane. It's almost upside down. This is 98 degrees to the ecliptic, and this is way more than we see for any of the other planets in the solar system. Secondly, its magnetic field. It's tilted massively, so it's 60 degrees offset from the spin axis and like shifted way down into the southern hemisphere. So very unusual. And what happens is that when we kind of look at how this magnetic field evolves, it gives us a very different kind of structure and variation to what we see at any of the other planets in the solar system. So we have this kind of really strange magnetic structure, and it's always presenting kind of a very different kind of part of the magnetic field towards the solar wind. So you have a lot of dynamics, a lot of kind of evolving interaction between the solar wind and Uranus. This is really also exacerbated by its extreme seasonal nature. So because it's got such a strong tilt, Uranus's seasons are incredibly extreme. You have regions around solstice where parts of the atmosphere are illuminated for decades on end, and others won't see the sun at all. And then when you go to equinox here, or in 2049 here, you have kind of very different magnetic interactions with the solar wind, which we'll kind of look at here. So when Voyager visited, it was more in its solstice season. It was rotating, showing mostly closed field lines here. But if we went to visit it in equinox around 2049, we see this very different geometry, this very different interaction with the solar wind. And that really has like a lot of effects on where we'd see the aurora, how this heating process might occur. And this is really kind of a thing we don't understand very well. And so it's an excellent reason to go visit. So there's a mission proposed, the next flagship mission, hopefully, for NASA, called Uranus Orbiter and Probe, which we're planning to go and visit in this 2049 region and visit Uranus during its equinox phase. And so before we kind of go to there, we want to have models of how we might expect the aurora to look like. And the first place to start really is with what we already know. And so this is from Voyager in 1986. This is ultraviolet aurora from molecular hydrogen. And you see these bright spots in the northern, so this is the northern magnetic pole and the southern magnetic pole. And you can see these are massively shifted from where the kind of geographic poles are at the top and the bottom of the plots here. But we don't really know what this might look like during equinox. So we have to take this and model it. And so what we have here is some currents that have been modeled into and out of the atmosphere, much like what we saw with Io and Jupiter during this 2049 equinox period. And so this is a measure of current versus latitude and longitude, and we see these auroral spots here and here, and we can kind of convert that into what we expect in terms of emissions and what that might look on Uranus's surface. So here we have some modeled auroral intensity kind of constantly spinning as the magnetic field spins with the planet. And it's going to be a real challenge to observe. But there's huge questions for a mission like UOP, such as what drives the aurora? Do we have this kind of internal driver like we do at Jupiter with Io, or is it more driven by the solar wind like we see at the Earth? How does the aurora vary over one day as it spins? With season, as we have this changing interaction with the solar wind? And how does this affect the heating? This is like a massively uncertain question. Uranus has been cooling continuously for 40 years, and we don't understand why. And then, final question, from more of like an engineering standpoint, is if we do go, how do we design an instrument that can best see these changes and see this hugely dynamic aurora and be able to capture it fully and get as much science out of it as we can? And so these are all things that we're kind of working on here in Arizona, and hopefully we'll continue working on those in the next 10 years, 25 years, 30 years. Space doesn't move too fast. Okay, so that's our kind of final stop on the tour, and Russell's somewhat satisfied for now, and he decides to journey home. And at this point, I just want to thank you all for listening and ask you if you have any questions. Yeah, down the front. Ooh, octagonal aurora at its pole. Which one's that? So I think you see like so to be fair, this my like expectation. So sorry. The question was asking about octagonal aurora at a pole of one of the planets, and you do see I guess like structures lower down in the atmosphere. Like the Saturn has like a hexagonal structure over its pole. So like my area of expertise, I guess, is more in the ultraviolet, which is kind of higher up in the atmosphere and more dictated by kind of the interaction with the magnetic field, whereas like lower down you see a bit more that's kind of driven by the middle atmosphere where you get more of these structures. So I tend to like sit a little bit higher. And so that's my kind of favorite part to talk about, I guess. Yeah, I'll have to look into it, but thanks. Thanks for the question. Anyone else out there? Down the back, yeah? So, okay, so conservation of energy. We have Io as the battery, Jupiter as the resistor. Who's losing energy? The question's a complicated one, and the answer probably is Jupiter at the end of the day. So, like, a lot of it is driven by like the rotation of Jupiter, and Jupiter has like a lot of internal angular momentum because it's just huge. It's massive. It's super heavy, and so it's that rotation of the magnetic field through Io's system that is really like driving those currents. So you're taking angular momentum from, I guess, like Jupiter's core or kind of lower atmosphere, putting that into Io, and then from Io you're kind of dumping that back into Jupiter's upper atmosphere. So it's a little bit more complicated than the picture I painted here, but yeah, this was nicer for, I guess, the storyline at least. Okay, yeah, back in.
Why is the magnetic system rotational axis off kilter?
Fine.
Why is the rotational axis and the magnetic axis off kilter?
Okay. Why are the magnetic and spin axes of Uranus so off kilter? That's a good question. I think it's one I probably should know more about, in fairness. So I think there are kind of theories about collisions occurring at some point, which kind of knock Uranus off its axis. In terms of the internal magnetic field offset, I'm not too sure. There's a lot of like heavy like dynamo calculations that people do about cores that I try not to get into. But yeah, I think at the moment still an unresolved question. But as with most things, collisions are a useful tool to or an excuse to not look at it any deeper. Okay, get back in.
So essentially, if it has an atmosphere, it's potential that it could have an aurora to some extent. Because the comet has no magnetic field, but it still has an aurora from the atmosphere temporarily.
Yeah, so, okay, so the question is, if you just have an atmosphere and an object, essentially, will it have an aurora? And so I think the question, like the answer to that is a bit more nuanced. So the really unique thing about comets is because that atmosphere is like constantly escaping, you can build that magnetic, like that electric field and that potential well over a really long distance. And so that can be 100 electron volts. And so that's enough to drive aurora. So typically you need something in the region of 20, 30 electron volts to start breaking apart molecules and driving emissions. At Mars, you can drive like a similar electric field, but because it's a much heavier atmosphere, much heavier planet, like your atmosphere is kind of a lot denser, a lot more condensed, and you don't have the potential to build it over such a long region, and so you only get maybe like 2 or 3 electron volts, and so they don't necessarily drive aurora in the same way. Mars has kind of different types of aurora, so you have like regions of crustal fields where you can drive aurora, a bit more structured like what you would see at Earth, and then if you have very strong solar events, you can see aurora on Mars where you just have basically these like incredibly energetic solar wind particles just like pummeling the atmosphere in these like unmagnetic regions, and that gives you kind of like a diffuse glow similar to what you see at comets, but it's, I guess, where the acceleration takes place. So for Mars, it's more at the sun, like that's where the energy kind of transfer is happening. For a comet, it's really like in the system where these electrons are being accelerated up to very high energies. Sorry, I think, is that... Okay, sweet, thank you. Great question. Yes? What's the most exciting thing about Aurora and what can it teach us? I mean, firstly, the view is spectacular. And whether you're looking at the Aurora like on a different planet, is something really cool. But yeah, for me, like the most interesting part is that like interaction between the solar winds and like the magnetic fields of planets, and how it's so the Jupiter, Saturn, Uranus, all of these planets are like 2-3 times hotter than we expect from solar heating. And so you're driving like a huge amount of energy into these planets, which we think is driven by the Aurora. For Saturn and Uranus, we're fairly confident. For Saturn and Jupiter, we're fairly confident. For Uranus, there's still a bit of a question mark. But like that kind of interaction, I think is just like fascinating, really. And so that's kind of what I enjoy looking at. Sweet, thank you.
Let's thank Peter again.
Thank you all.
All right, so just like before, whoever won the trivia, come find Sully in the back. Thank you all for coming. And we will see you back here April 15th for Space Drafts 116. Same time, same place.